All right, welcome. Today, we're going to build a network from the ground up, but we're going to focus on the critical security choices you absolutely need to nail for your exams. Think of this as your secure network blueprint. So here's the big question, right? This is the fundamental challenge of networking today, because with all this amazing connectivity, well, that comes with a whole lot of risk. Let's start by defining exactly what we're up against. The second you connect one computer to another, you open the door to all these inherent vulnerabilities. Your data is suddenly way more exposed, malware can spread like wildfire, and everything can grind to a halt. A truly good network design has to tackle every single one of these risks head on. So here's our game plan for this revision guide. We're going to hit 5 key areas. We'll start with the foundational structure and work our way all the way up to the digital shields and armor you'll need to know about. Okay, let's get right into it. Our very first decision is choosing the fundamental layout of our network. You got to get this right, because it's the bedrock that everything else is built on. So right off the bat, you've got this massive security trade-off to think about. On one hand, you have the client-server model. It's centralized, which makes it more secure and way easier to manage. But it's expensive, and that central server becomes a huge single point of failure. On the other hand, peer-to-peer is cheap and more resilient if one machine goes down. But the security is, well, it's pretty weak, and good luck trying to trace files. Okay, first up is the bus topology. Think of this as the simplest, most basic setup. All the devices are hooked up to one single cable, the backbone. It's cheap, for sure, but that backbone is a massive vulnerability. If it breaks, the entire network is kaput. And here's the real kicker from a security perspective. All the data is visible to every single computer on the line. Not great. Now, moving on to a star topology. This is a big step up in terms of robustness. Each device gets its own dedicated line to a central point. If you're wired, that's usually a switch. For Wi-Fi, it's a wireless access point. This means you get way better performance, and if one cable fails, only that one machine goes offline. The downside? You've just created a new critical point of failure, that central device. And then you have mesh, which is pretty much the king of resilience. Every device connects to several others, creating all these different paths for data to travel. It's self-healing, which makes it absolutely fantastic for wireless networks. But it can get really complex and pricey to manage, especially if you're trying to do it with physical cables. Okay, so we've got our blueprints. Now let's talk about the actual hardware, the nuts and bolts that bring these networks to life and actually control the flow of all that traffic. Every single device that wants to connect to a network needs a network interface card, or NIC. The best way to think about the NIC and its unique hard-coded MAC address is like a permanent, unchangeable fingerprint for your computer on a local network. Okay, this is a super important distinction for your exams. Switches and routers, they have totally different jobs. A switch is like a local traffic cop. It uses those MAC address fingerprints to direct traffic within one single network. A router, on the other hand, is like the major highway interchange. It uses IP addresses to send data between different networks, say from your home network out to the big wide internet. So what happens when two networks are basically trying to talk to each other, but they don't speak the same language? They don't use the same rules? Well, that's what a gateway is for. It acts like a universal translator, stripping off the old protocol info from a data packet and sticking on a new header so it can be understood on the other side. You can have all the best hardware in the world, but if the devices can't speak a common language, it's all useless. That's where protocols and standards come in. They are the essential rules of the road that allow any device from any company to communicate with any other. They're absolutely vital. All right, for your exam, you absolutely have to know the difference here. It's all about a trade-off. TCP is all about reliability. It establishes a connection first, checks for errors, and makes sure every single piece of data arrives perfectly. It's like sending a registered letter you can track. UDP, on the other hand, is about speed. It just throws the data out there with no guarantees. It's like shouting across a room. Perfect for live video or gaming where a tiny glitch is better than a long delay. It's easy to take for granted, but without the DNS, the internet as we know it just wouldn't work. Can you imagine having to memorize a long string of numbers for every single website you wanted to visit? It'd be impossible. DNS is that crucial phone book that translates the easy domain names we use into the IP addresses that computers actually need to find each other. Okay, so we've looked at the layout, the hardware, and the rules. How does it all actually work together? Let's follow a single piece of data on its journey from your computer out across the network.
So your data starts its journey by going down this 4-layer stack. At the top, the application layer picks the right protocol for the job, like HTTP for web browsing, FTP for file transfers, or SMTP for sending an email. Then, the transport layer chops the data into smaller packets. Next, the network layer slaps on the final destination IP address. And finally, the link layer adds the MAC address for just the very next hop on the journey. This whole process is called encapsulation.
And this is a perfect way to picture what's happening. Your original data, right there in the middle, gets wrapped in all these different layers of information. It's almost exactly like putting a letter in an envelope and then putting that envelope inside another, slightly bigger one for the next part of its trip.
Okay, so we've got our packets. How do they physically get from A to B? The old school method was circuit switching. Think of it like the old telephone system creating a dedicated private line just for your call. But the internet uses packet switching, which is way more efficient and resilient. Each little packet can take the best route available at that exact moment. And if one path gets blocked, the others can just be rerouted on the fly.
All right, we've built the network, we know how the data moves. Now for the most important part. Let's lock it down. We have to defend the perimeter with things like firewalls, but we also have to protect the data itself while it's in transit. And that's where tools like proxies and encryption become absolutely essential. Think of a firewall as the bouncer at the door of your network. It stands at the border and it inspects the ID of every single packet trying to get in or out. It checks things like where it's from, where it's going, and what it's trying to do. Then, based on a preset list of rules, it makes a simple choice. You're in or you're not. Now, a proxy server, this is like adding a secret agent to your security team. It acts as a middleman. All your web traffic goes through the proxy first. This is fantastic for anonymity because it hides your real IP address. It can also speed things up by storing or caching copies of popular sites. And it gives network admins a really powerful tool to filter content and cut down on traffic. Okay, let's wrap this up with a quick revision checklist. The big takeaway here is that network security isn't just one thing. It's a whole system of layers. Every single choice, from the physical layout you pick, to the hardware you use, to the software defenses like firewalls, proxies, and encryption, all play a critical role in building a strong layered defense. So I'll leave you with one final question to think about for your revision. With all of this incredible, complex technology designed to protect us and our data, what is ultimately the weakest link? Is it the hardware? Is it the software? Or is it the human user sitting right there at the keyboard?